Okay, so today we're going to talk about 2.2. Again, the book that you're using may be the one that is the Stewart edition. You also may be using the Briggs edition. So just depending on what it is, don't freak out too much about the numbering of it. So right now it says 2.2, but the most important thing when you're doing your homework is that you're doing the sections in chapter 2 that talk about the limit of a function or something. So don't stress if it's like not perfectly lined up with the order of the book. You'll see some of the sections like are 2.4 in one book, and the other book it's 2.7 or 2.6 or something. So it'll be okay. I'll try to fix it for those of you taking it from a different book. So it says we're going to talk about the limit of the function in all of chapter 2 and then kind of work into derivatives from there, which are defined by limits. So we say, given f of x is equal to x minus 1, what value or number does y or f of x approach as x gets or goes to 4? So here's the thing with limits. Basically, what limits are saying is that you never actually make it to the number, but you get so close you basically can't tell the difference. There's a lot more to it than just that, but the idea of infinitely close is what we're going to work with. And then in another section, we're going to talk about the precise definition of limit, and you guys will kind of see how it works with epsilon delta proof, or I'm sorry, epsilon delta definition of limit. I guess it's a proof too. So basically, what we want to know is in the previous section, we were doing limits, but we weren't calling them that. We were basically working with the slope of the tangent line, and we couldn't really find it. So we had to pick up the secant line and move it closer and move it closer and move it closer. And then we could just keep doing that. And then at some point we had to kind of say, you know what, I feel like this is the value it's approaching, even though we never made it there. So that's the idea behind limit, is I feel like this is the value we're approaching even without making it there. So in this particular problem, we want to know, what is my graph approaching? So kind of a simplified way to think about limits in this particular setting is when you're trying to find the limit of a function, what you're really talking about is basically the height of the function. You're saying what is the height of the function approaching as the x value approaches a certain number on the graph. So as your function gets an x value, I guess you could say plugged into it, or it's approaching that number, what is the height of your graph approaching? What is the height of your function approaching? So for this one, they want us to do this little dance around 4. So I'm going to set up these tables just like we did in the previous section. And again, this isn't ideal. This isn't the best way we want to do it. We want to graduate onto something a little more advanced. So we're going to say, okay, when I plug 3.9 into this function right here, okay, when I plug 3.9 into there, I should get 3.9 minus 1, so I should get 2.9, right? Then when I plug 3.99 into there and I minus 1, I should get 2.99. And then this should be 2.999, right? And then we do the same thing over here. We get 3.1. 3.01, 3.001. So I want you guys to notice that in this particular problem, we're approaching 4 from the left-hand side. So imagine if this is 4, here's 3.9, right? Well, that's a little weird to look at. So let's say like here's 3.9. So then here's 3.99. So then here's 3.99. You get the idea? And then over here, we're going to come from the other side of 4. We're going to say 4.1, oops. We're going to say 4.1, 4.01, 4.001. You guys get the idea, right? So we're doing this little dance where we're getting closer and closer on each side. So we're seeing from the left side, like let's say that this is 4 right here. So what height are we approaching over here? And then what height are we approaching over here? And it looks like the height is going to be, as we approach it, actually, I see a better way to do it. We just do this like, oops. So what height are we approaching? Well, it looks like we're approaching a height of 3, right? Because this is 2.999 and this is 3.0001. So more than likely, this graph is approaching a height of 3. So we're going to say that this limit is 3. So we're going to come over here and we're going to say the limit, this is how you formally write it, the limit as x approaches 4, so right here, this down here below the limit will tell you what you're approaching, and this is the function, this is your f of x, right? And it says the limit as x approaches 4 of x minus 1 is equal to 3. But in general, what it's saying in a simplified version of it is this is the height we're approaching, okay? So here's the formal way we say it. The limit as x approaches a, x approaches a of f of x equals L. And then this is the notation we're going to use from now on, okay? So from now on, this is our notation that we use to talk about the limits, okay? Inside the f of x, you notice that is the function. X approaching a is the value on the x-axis you're approaching, and L is the limit, and in these problems, the simplified version of it is the height that you're approaching, okay? So there's also something called left-hand limits and right-hand limits. Okay, so this notation right here, I want you guys to look at this little minus sign and this little plus sign. That does not mean that it's a positive or negative number. What it means is you're coming from the left side of that number or you're coming from the right side of that number. So as you notice here, it says the limit as x approaches a with a negative sign on the like exponent version of it. That means the limit as x goes to a from the left, okay? So think of it as x is less than a. Okay, so it's to the left side of that. And then this is the limit as x goes from the right side. So this is coming from the right. So you think of it as greater than a little bit on the side of it, okay? So this leads us to what I call the true limit or the pure limit. In your book, I think they call it the full limit. I sometimes call it the true limit, okay? So the full limit, in order for the limit, I think they just call it the limit. So in order for the limit to exist, the left-hand limit and the right-hand limit have to approach the same number. So what this means is that the limit as x approaches a of f of x, equals L if and only if. So this is how I write if and only if, is with two F's. So if and only if, and if and only if means, I guess it's similar to saying to an equal sign, okay? So we say the limit as x approaches a from the right of f of x equals L, and the limit as x approaches a from the left of f of x equals L. So what this means is this kind of goes, remember, if it's an if and only if statement, that means that it's a two-way street, okay? So a two-way street means that if the limit is equal to L, then these two things must be true, okay? But it also means if these two things are true, then the limit must equal L, the true limit. So it's a two-way street, meaning you can go forwards and backwards. Now think of things that aren't two-way streets. So you could say, for example, if it is a rectangle or if it is a square, then it is a rectangle. Okay, so that goes, if it's a square, then it is a rectangle. However, you can't go backwards and say, if it is a rectangle, then it is a square. So that is not a two-way street. So that's why it doesn't have if and only if. In this problem, they're saying if and only if because they want you to know that if you know that this limit exists, then that means the left and right hand limits were the same. And likewise, if the left and right hand limits are the same, then the true limit exists and it was L, okay? So let's look at this real quick. Okay. So what I'd like you to do is to consider, just for an example, consider f of x equals sine of 1 over x, okay? What is the limit as x approaches 0 of f of x? Now notice you can't just plug 0 in because you take the sine of 1 divided by 0, but dividing by 0 is undefined in our math classes, okay? And again, undefined doesn't mean undoable, impossible. It just means in the real numbers, we don't have a definition for that. We don't know how to deal with that, okay? So what I'd like you guys to do is I'm going to have you draw some tables. And let's go one from the left-hand side of 0. And let's go another table from the right-hand side of 0. And I'd like you to use these numbers and plug them in your calculator. Let's use negative 0.1, negative 0.01, negative 0.001, negative 0.00001, and then a whole bunch of them. 1, 2, 3, 4, 5, 6. Let's go 7. Okay, and then over here, we're going to do the positives on the right side of 0. So positive 0.1, positive 0.01, positive 0.001, positive 0.0001, and then positive 0.0000001, I think. Let me see, 3, 6, 7, yeah. Okay, so I'd like you to pause the video and see what value you approach from the left and the right side, okay? Okay, so hopefully you guys have unpaused the video, and you should get approximately 5.44 here, 0.506 here, negative 0.8268. So now you might be thinking, oh, we're approaching like -1 or something maybe, because remember that sine of x is bound, sine of 1 over x is bound between -1 and 1. So I know none of my answers will be smaller than -1, and none of my answers will be larger than 1. So I'm thinking, oh, maybe it's approaching -1. And then it switches, oops, did I skip one? No, it switches to negative point. Oh, I messed up. I think I'm missing one. 1, 2, 3. 1, 2, 3. Yeah, hold on, guys. I'm sorry. I'm missing one of the sets of zeros. So we have to do 3 zeros, negative 0.0001, then 4 zeros. Yeah, and then 7 this time. Seven zeros. Okay, so then we have 0.3056, negative 0.03575. And this is from a computer program, so it's a little bit more accurate than the calculator. And then negative 0.93164. And then let me fix this one over here now, 0.0001, 0.00001, and 0.0000001. Okay. And then over here, we get negative 0.544, negative 0.506, 0.8268, negative 0.3056, 0.03575, and 0.93164. So what you notice is we're supposed to, like up here, we're supposed to be approaching the same number from the left and the right. But as we go over here, yes, they're kind of mirrored, but you see this is a positive and this is a negative. So they're not actually approaching the same number. And in fact, from either side, they're not approaching a number. Look, as we get closer to 0 from the left, it's not like there's a consensus. It's alternating between positive and negative, so that's not doing it. And then as we go from the right, it's doing the same thing, but from negative to positive. So it's kind of hard to tell. Again, I can't draw it too well, but it would look something like this. Again, I can't draw. So here's +1, here's -1. And it kind of does one of these. Okay, and then as it gets really close to here, oops, geez, it starts going up, and then down, and then up, oops, all the way to 1, and then down, and then up, and then it goes real fast. You can't even see it anymore. And then it comes back out, and then it goes over to here. Okay, so it's oscillating faster and faster and faster as you zoom in. So this particular problem has no limit, because in order for the limit to exist, it has to approach the same number from the left and the right. So we say the limit as x approaches 0 of sine of 1 over x equals dne. Does not exist. Okay. All right, so let's take a look at another limit. so, and then in the next section, okay, so let's do this one. So we have the limit as x approaches 2 of x cubed minus 2x squared all over 3x minus 6. So now I don't want to use a graph anymore, and I don't want to use a table anymore. I want to actually see what I can do. So let's see, maybe this one won't work, but I just want to take a look. So one of the key techniques that I'm going to use is factoring. So I'm going to try to factor. I'm going to factor an x squared out of here. And I am going to get a x minus 2 right there. And then I'm going to factor a 3 out of here. Oops, sorry guys, I'm making a mistake. So I'm going to say the limit as x approaches 2 of x squared times x minus 2 divided by 3 times x minus 2. So we get our x minus 2's to cancel. And we're left with the limit as x approaches 2 of x squared over 3. Now, in general, when you're dealing with rational functions and polynomials, they are continuous on their domains, and you are allowed to use limits. So you're basically saying as x approaches 2, right? You're not saying you actually made it to 2. You're saying x approaches 2. So if x approaches 2 in this function, so you could go 1.999999 squared divided by 3, and then you could do 2.000001 squared, just to kind of in your mind see what's kind of happening. But when you're dealing with polynomials and rational functions, if the value that you're working with, the limit as x approaches a, is like a number that does not make the value undefined and is not a vertical asymptote, then you're allowed to just plug it in. And you're allowed to say that this limit is 4 over 3 because I plug 2 in and I get 2 squared is 4. So this works really well with polynomials especially, and then also rational functions and other things on their domains. Okay, so we'll talk about that much more when we hit continuity as well. All right, so factoring is a big key. So factoring can be very helpful when dealing with rational functions, which this was originally. A polynomial divided by a polynomial is called a rational function when dealing with rational functions. Okay, so just keep that in mind. You're never going to get away from factoring. It's always going to come back. So our limit was in fact 4/3. Okay, and that means that this function approaches the height of 4/3 as x approaches 2. Let's look at a piecewise function. So let's evaluate this one. Evaluate the limit as x approaches 0 of f of x when f of x equals, and then let's do a piecewise, x plus 3, 1, negative x minus 1, and then we have x is less than 0, x equals 0, and x is greater than 0. Okay. All right, so they want to know the limit. So in general with piecewise, so in general with, now this doesn't mean for all time, but this is just kind of your standard way to think about it. With piecewise, functions, you will need left and right hand limits. Okay, so in general, all right, so let's take a look at this. If I want to find the limit as x approaches 0, I have to come from the left and the right of 0 because these are all different graphs depending on which one you're working with. So we're going to take the limit as x approaches 0 from the right. of f of x. So which one of these is from the right of 0? Well, that would be this one, right? Because it says x is greater than 0, so we're going to use that guy. So I'm going to say the limit as x approaches negative x minus 1. Okay, so in that particular problem, that'll be my f of x. So when I plug 0 in there, because this is a polynomial, I'm going to get 0 minus 1, which would be negative 1. Okay, now I'm going to do the limit as x approaches 0 from the left. Limit as x approaches 0 from the left of, now we have to find which one of these is to the left of 0. So this one will be to the left of 0. So that will be x plus 3. So when I plug that 0 into there, I'd say 0 plus 3 equals 3. So these are my two limits of my left and right hand limits, okay? Now here's the problem. The limit, the true limit, as x approaches 0 of f of x itself equals dne. And by showing me that the left-hand limit is negative, or I'm sorry, the right-hand limit is negative 1, and the left-hand limit is 3, you are showing me that you know this property up here that says that the full limit, in order for the full limit to exist, or the true limit, the left and right-hand limits have to approach the same number. In this case, they approach negative 1 and 3, which is not the same number, so the limit, the true limit, does not exist. Now, did the left-hand limit exist? Sure, it was 3. Did the right-hand limit exist? Sure, it was negative 1. But the true limit did not exist, okay? So there are cases where the true limit doesn't exist, but the left and right-hand limit do. Okay, so let me get a graph for you guys now. So there's quite a few graphing problems in the homework. These are really good to help you understand limits. Okay, so let me draw, let me try to draw the best I can. Okay, so let's say we got 2 right here, and I'm going to draw this little smooth curve, and then I'm going to have this one up here. I'm going to draw this. Okay. And then let's do a little closed circle there. And then let's do an open circle here. No, you know what? Let's go from here. Open circle to here. Okay. And then let's put one right here. Okay. And let's call that, well, I don't know. Let's call this 5. Let's call this 6. Let's call this 8. Don't worry about my measurements seem off, obviously. Let's say that this is 2. Let's say this is 1. Let's say this is 3. Let's say this is 4. And 5. And that should be good. Okay. So I'm going to ask you a bunch of questions about this now. So let's find, so the limit, let's call this number 1. The limit as x approaches 2 from the right of f of x. Let's say the limit as x approaches 2 from the left of f of x. And let's say the limit as x approaches 2 of f of x equals. Let's do number 4, limit as x approaches 4 from the right. Let's do 5, the limit as x approaches 4 from the left. And let's do the limit as x approaches 4. And let's do 7. And let's do 7 is f of 2. Let's do 8 is the limit as x approaches 3 of f of x. And let's do number 9, limit as x approaches 0 from the right of f of x. Okay, so let's take a look at this now. So I have all these questions I want to talk to you guys about. So for the first one, it says the limit as x approaches 2 from the right. So what we do is we find the number 2, so we're here, right? And then we're going to look up And we're going to come from the right. So think about it like this. You're walking on your graph, you're walking on your graph, you're walking from the right-hand side of 2. And as we get really, really close to 2 as our x value, what is our height approaching? Well, it kind of looks like, I mean, I guess if we look over here, let's call that 3. So it looks like we're approaching a height of 3 from the right-hand side, okay? Now we do it from the left-hand side. So I'm walking, I'm walking, I'm walking. Now I'm getting closer and closer. What height am I approaching? It looks like a 3. Now notice I'm not actually touching the value of 2 because I never get to make it to 2. And also, I never make it to the height of 3. I'm approaching the height of 3, okay? So now we say the limit of f of x as x approaches 2. Well, this is the right-hand limit, this is the left-hand limit, and they're the same number. So then the limit exists, and it is 3, okay? Now, again, that's kind of weird because right here, it's 5. So we just got to keep in mind that the limit does not have to be defined. You can approach an open circle, meaning it's undefined at that location. So the limit as x approaches 4 from the right. Okay, so let's come over here. So we're trying to get to this value of 4, right? So we're going from the right-hand side of 4. We're going from the right-hand side of 4. What height does this look like we're approaching right here? It looks like a height of 8. Now we're going to go from the left-hand side of 4. So we're here, you know, we're coming over here. We hop up here, hop back down, and we're getting closer and closer to 4 from the left. What height am I approaching? Remember, I never get to make it to that little closed-in circle. I'm approaching, what does it look like? A height of 5, maybe? Oh, no, that looks like a height of 6, actually. Let's say that's 6. Let me see. Oops. Yeah, it's about 6. I mean, I'm off by a little bit, but you guys get the idea. Let's say that it approaches about a height of 6. Now, because it approaches a height of 8 from the right and a height of 6 from the left, that means that the true limit is DNE. So this is a good way you can tell if a limit truly exists by checking from the left or from the right. Now they want to know, what is f of 2? Well, f of 2 means no limits. You're actually plugging 2 into this function. Well, when I plug 2 in, it doesn't exist right here, but it does exist right here, right? So my height is 5 at f of 2. This is not a limit. This is just basic algebra. From f of 2, our height is 5. Okay. So our height is 5. Okay. Now we do the limit as x approaches 3, just straight up 3. Okay, so now I'm going to use a different color. They didn't ask me for left and right, but I'm going to do left and right. So here's my 3, right? So I'm here somewhere. What height does this look like I'm approaching? What is that? You going to say a 4 maybe? Because look, I'm right here. I'm walking. I'm getting closer to this. I'm coming from the right-hand side. I'm getting closer to this. So I'm going to say that's about a height of 4. So I'm going to say my height is 4. My limit as x approaches 3 of f of x is 4. And it approaches the same height from both sides, okay? Now we do the limit as x approaches 0 from the right of f of x. Well, 0 from the right, that's going to be right here, right? I'm getting closer and closer. I'm going to get right here. Here's 0. So I'm getting closer and closer and closer and closer to 0. I never get to make it there, but what does it look like my height is? It looks like my height is 2. So this is how you can interpret limits graphically. And this should help you also understand when you're doing algebra. It also should help you understand what height you're approaching, okay? So remember, for now, limits in a simplified version is the height of the graph and what we're approaching. So hopefully that helps you guys. There's quite a few homework problems on that, so please give it a shot. It's a good way to kind of understand ideas for that. Thanks for watching, and I will see you in the next meeting, or I will have another video for you.